Greetings, folks. Although it probably isn't obvious when you first start to run into them, potential energy functions are really nothing more than mathematical contrivances that are designed to do one thing and one thing alone, and that is to do work calculations. This video is going to derive for you the potential energy function for gravity, and then I'm going to speak a little bit about potential energy functions in general.
So we're going to deal with gravitational potential energy, and we're going to start with a very simple question, and that is, how much work does gravity do as a body moves from one point to a second point in the gravitational field? And I'm going to identify where point 1 is with the coordinate y1 and where point 2 is with the coordinate y2. To do the work calculation, we're going to take F dotted into D. The magnitude of F is going to be mg. The magnitude of D is going to be y2 minus y1. That's this distance here. And the angle, the displacement is going to be up. The force of gravity is down, so the angle is going to be 180 degrees. So here we have all of that written out. If we put in the minus 1 for the cosine of 180 degrees and we distribute the mg through, we end up with this relationship. So at this point we have to take a detour and ask the question, what would have happened if we hadn't gone from A to F in doing our work calculation, but instead had gone from A to B to C to D to E to F? Would the amount of work that gravity did, would it have changed if we had taken this more circuitous route? To start the process, let's see how much work gravity does or would have done if we had gone from A to B. So the amount of force in the dot product would have still been mg, the displacement would have been d1 as I've defined it here, and the angle between the line of D and the line of mg would be 90 degrees. Cosine of 90 degrees is 0, which means apparently gravity would do no work as the body went from here to here. Same thing going from D to E up here, no work being done by gravity. Going from C to D, the amount of work gravity would do would have been negative, displacement up, force down. Going from E to F, the amount of work gravity would have done would have been positive, displacement down, force down. The magnitudes would have been the same, but because they were opposite signs, when you added them together, they would have negated one another. So their contributions would have gone to 0. And the only net work that wouldn't be either negated or just be 0 would have been the work done as the body went from B to C, which is the same as the amount of work that was done when we went from A to F. What's interesting about this is that it means that apparently the amount of work that's done by gravity as you go from A to F is path independent. It only depends on the endpoints. It doesn't matter what path you take as long as you end up at F. Forces that act this way are called conservative forces.
As a side note, friction is an example of a non-conservative force. Almost always friction is opposite the displacement, which means the amount of work that's done is going to be negative. So the further you travel, the more negative work is going to be done, which means if you go a circuitous route versus a straight route, you're going to do more work on the circuitous route. The amount of work that's being done is not endpoint dependent, which is the characteristic of a conservative force. Friction is a non-conservative force.
But getting back to gravity and conservative forces, if all that matters is where you start and where you end, we should be able to come up with some kind of function that defines a number that we can attach to the initial point and a number that we can attach to the final point that has the characteristic of being such that when you take the difference between the two, it tells you how much work that conservative force, in this case gravity, actually did. What's cool is that having already done the work calculation, we have a function that will do that. mgy2 is the function mgy evaluated at y2, the second point. And the same is the case with mgy1. It's the function mgy, where y is the coordinate of the point of interest, evaluated at y1. We're taking the difference between the two. That's associated with the amount of work gravity did. The only thing that's tricky is that we have to manually stick in a negative sign for this to work. This function, mgy, is called the potential energy function for gravity. The symbol that's used for potential energy functions is a U. So if I wanted to identify the gravitational potential energy function, I would write U sub g equals mgy. So in general, every conservative force has a potential energy function associated with it. We may not know what that potential energy function is, but every conservative force has the possibility of a potential energy function. That potential energy function will be such that if you evaluate it at the beginning of the interval that you're interested in, and you evaluate it at the end of the interval that you're interested in, and you take the difference between those two quantities and stick a negative sign out in front, it will tell you how much work that force function did as the body went from point 1 to point 2. Or written out shorthand, the amount of work that the force field did will equal minus the change in the potential energy function. This is the only thing you will ever use a potential energy function for, ever. Potential energy functions are mathematical contrivances that are designed to allow you to do work calculations. That's all they're good for. The amount of potential energy an object has at a particular point has no significance, no physical significance. It's only when you take the change in the potential energy between 2 points that there's physical significance. And that physical significance is when you've taken that change and you stick a negative sign in front of what you end up with, that tells you how much work that force field did as you went from the one point to the other. So if we take what we now know about gravitational potential energy and go back to our original problem, we would identify the gravitational potential energy function as mgy. We would evaluate it at y1 and y2, which would give us these values. And we would proceed to use the relationship. The work that gravity would do would equal minus the change in the gravitational potential energy function. That equals minus u2 minus u1, which is minus mgy2 minus mgy1. Quick and easy. No problem. Potential energy functions in general are a great way to figure out work if you know what they are. Anyway, that's it.